was you. Who left? All right, so today we are starting with exponentials. So it's a new unit. We'll be looking at exponentials and logarithms. So we're going to start today by graphing some exponential functions. So our basic exponential function looks like this. It is f of x equals b to the x. And that b is a different b than the one that we use for transformations, which sometimes can get things a little bit confusing, but that b stands for base, all right? And so basically we have an infinite amount of parent functions. Really, they all pretty much look the same, but the exact anchor point values change depending on what the base is. Most of the time when you want to represent an exponential function kind of as a parent function, usually we use 2 and 1/2, but really they could be anything. So let's try and graph this based on what we already know. So we're going to substitute in a couple of points. If x is 0, so if I take 2 to the 0 power, what do I get? 1. Anything to the 0 power is 1. So then if x is 1, that would be 2 to the first power, which is 2. If I use -1, 2 to the -1 power, what's that? 1/2 with a question mark? Yes, you're right. Because if I have 2 to the -1 power, remember what negative exponents do? It brings it to the denominator, so it's 1 over 2 to the first then. So basically, if it's just to the -1, you're taking the reciprocal is the way that works. Okay, so I've got those 3 points. I mean, pretty much, you know what exponential growth looks like. It's a whole, those terms are used a lot. And so I know that this is going to keep increasing. Well, this is going to clearly keep getting smaller, but is there anything I could substitute in for x that would give me 0 as an outcome? No. So it's going to be really, really small, but it's not going to get to 0. So I have an asymptote here at y equals 0, and my function looks like this. Okay. So that's when b is greater than 1, right? So we have that, where it's greater than 1. But if it's less than 1 or greater than 0, so basically it's a fractional amount, less than 1, then let's plot some points over here. If I take 1/2 to the 0 power, what do I get? 1, right? Anything to the 0 power, except 0 is 1. Then if I substitute in 1, 1/2 to the first power is 1/2. If I substitute in a -1, what do I get? 2, because it's the reciprocal. All right, so again, if my exponent keeps getting bigger and bigger and bigger, my y value will get smaller and smaller and smaller, but will I ever reach 0? No. So I have an asymptote here at y equals 0 as well, and this looks like this. So basically, these are reflections of each other in the y-axis. And I don't like the wording down here, and I didn't reword it, and I wish I had. So we're going to mark out this when a is greater than 1 and, because that's not really a great way to say it. And even saying b is less than 1, it's the absolute value of b. But anyway, so if this is a number greater than 1 and everything's considered absolute value, so we really should, let's put a little absolute value around b, it'll make me feel better. It's just a really bad statement here. So increasing, which is exponential growth, decreasing, which is exponential decay. Okay, so shouldn't be a brand new concept for you. All right, so let's talk about the natural base exponential function. Okay, so we have e. This is a lowercase e, usually looks like it's cursive. It represents a number. It is an irrational number. Remember, irrational number means that I cannot express it in the form of a fraction. And e is much like pi. You see I have my pumpkin pie shirt on for Halloween. So pi is an irrational number also. E is an irrational number, comes from a different place, does different things. If you're not very familiar with e, on Monday we're going to watch a little short, 2-minute video that kind of explains it a little bit better with what we're doing on Monday. So just hang on right now and trust me, and we'll get there. But it has an approximate value of 2.71828. Blah, blah, blah. And it keeps on going, just like pi keeps on going. Now, you're not expected to know like all the decimals, just like you're not expected to know all the decimals of pi, although there are people that know quite a few of them. I did have students one year that their homeroom, so one of those times where we went to homeroom a lot and we did absolutely nothing, so we just sat there, but she had a pi border around her room that had like the first 50 digits of pi, and so they literally just sat there and stared at it, so they kind of memorized it without intending to memorize it. But one kid could give you the first 50 digits forwards and backwards. He did it in class. We made him turn around and close his eyes, and he rattled them off. It was amazing. So I don't know, he can impress people at parties. I don't know if that helps him with anything else, but my brain doesn't work that way, so I don't know. Yeah, I know pi. You want to hear it forwards and backwards, and everybody would be like, wow, yeah. That's how you actually impress people at parties, in case you didn't know. So anyway, exponential functions with base e. So if I have a base e, these are called natural base exponential functions. So instead of the b being 2 or 1/2 or whatever, that base would be e. And then it says many real-world applications of exponential functions use base e. And so that's what that little... There are tons of videos out there that give good explanations, but most of them are so long. This one that I feel like gives a good, concise explanation kind of makes more sense to go with what we're doing on Monday, but it'll make all this make sense too. All right, so that means it looks like this. F of x equals e to the x. So just like pi, you need to know the basic value of it. I mean, a rough estimate for pi would be 3. 3.14 is also an estimate to get you, so that you know it's a little bit more than 3, but you would never actually use 3.14 to calculate anything. You would use the pi button. So same with e. You would use the e button if you're going to actually calculate something, but we do need to have a basic understanding of the value so we can graph and do some other things. So e is about 2.718 blah, blah, blah. So what needs to be in your head for sure is 2.7. Like, that's an estimate. That is not the value of e, but especially with graphing on here, 2.7 is close enough, right? We're also going to need to know what 1 over e is, or e to the negative 1 power, I guess. Same thing. That's about 0.36 something, 7879, 78, blah, blah, blah. So in your head, we can just have 0.37. So you have 2.7 and 0.37 for the two values of e that you just kind of need to know so that you can function with it. Right? So let's graph some things here then. So it says, given the function f of x equals e to the x power, we're going to graph that, and then we're going to identify its characteristics. So I'm going to start with an x value of 0. If I take e to the 0 power, what do I get? 1. Exactly. If I use 1, e to the first power is about 2.7, so I go to about 2.7. Graph that. E to the negative 1 power is about 0.37, so I go up about a third of the way. And just like with the other ones, the smaller and smaller and smaller this number gets, I'm going to get closer and closer to 0, but I'm never actually going to get there. So I have this. My function looks like this. So it's the exact same concept and the exact same shape as your b to the x up there when it was 2. It's just like instead of 2, it's e, or it could be 3 or 4 or whatever. Same ideas. So since I'm increasing, this is exponential growth. My domain is all real numbers, so I'm negative infinity to infinity. My range goes from 0 to infinity, and I don't include 0 because it's an asymptote. Your y-intercept for your parent function of no matter what the base is, you're going to take it to the 0 power, so it's going to have to be 1, so it's 0, 1. My asymptote is y equals 0. So my end behavior, I took out the infinities that were here because we need to start thinking about what really goes there. And in this case, it is infinity. X is going to actually be able to approach infinity, and it's actually going to be able to approach negative infinity, right? So as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, what does f of x approach? As x approaches negative infinity, f of x approaches 0. What questions do we have? Anything? All right. So let's talk about some transformations. So here's a little, it says recall, meaning we already know this, recall the transformation rules. Now one thing that looks a little different on these is that instead of using A, B, C, and D, there's an H and a K in here, but they do the exact same thing. And I left it in here like this because you could see it either way, right? And it really doesn't matter, because all that matters, whether this is an H, whether this is a C, whether it's a Q or a picture of a bunny, it doesn't matter. It still represents a shift to the left. I mean, it doesn't matter what it is. We just have to use a variable for that. What gets a little confusing on this is that, like I said before, this B is a different B, but if you don't think about them as letters and just know what happens when it's in that place, you're fine, okay? So it's all the same stuff. Probably don't even need to look at that. So we're going to identify the parent function and describe the transformations. So on number 1, I look for the base. So to identify the parent function, that's what it asks for first, it's going to be f of x equals something. The base of the exponent is 4. So it's 4 to the x. That's the parent function. Can I multiply the negative 3 times the 4 and just go ahead and make that 12? No, that's a big fat no. Aunt Sally would be really upset with that. Okay, and then, so that means that this is exponential growth. It basically looks like this. So then I look at all the other stuff going on to figure out how many transformations I have. Well, I have a negative, I have a 3, I have this negative 2, and this negative 7. So that's a total of 4 things that I need to talk about. With the exponentials, it's way easier to tell if something affects x or y, because if it affects x, it's in the exponent. So it's really easy to separate that out. So this negative here, a negative, no matter where it is, always means I'm doing what? Reflecting. So I'm going to have a reflection in, and so this affects y since it's not in the exponent, which means it's a reflection in the x-axis. Then I have this 3. The 3 is being multiplied out front. It affects y, so that means it's a vertical what? Stretch. Yes, vertical stretch by 3. Then I have this x minus 2. What does that tell me I do? Right, 2. Good. And then that 7 means I go down 7. Any questions at all? Same transformations we've been doing, just for the different function. So that's why they're so important, because you can apply them to pretty much anything. All right, so then let's look at number 2. So I first have to find the parent function. So that's f of x. The base of the exponent is e, so it's e to the x. Still looks just like that with a little sketch. Then I need to figure out how many transformations are happening. I have a 4/3, a negative, and a 5, so that's a total of 3. That 4/3 is being multiplied out front. It affects y, not x. So it's a vertical. Would this be a stretch or compression? Stretch, because it's greater than 1 by 4/3. I have a negative up there. Negative means I reflect. Would I be reflecting in the x-axis or y-axis? Y. Very good, because it affects x, so it's in the y-axis. And then that 5 at the end means I go up 5. Any questions? Same old, right? We're going to skip to number 4, because we definitely don't need to do all of these. We're going to do number 4. All right, so I identify my parent function. F of x equals, the base of the exponent is 3/4. Now, anytime the base is a fraction, you have to put it in parentheses. Otherwise, that x would just be an exponent on the 3, and that would be a bad thing. And since this is less than 1, this is decay, and it would look something like that. Then I'm going to count them. I've got a negative, a 3, a 2, and a 1, so that's 4 things I need to talk about. This negative means I reflect. So this is a reflection in which axis? X or Y? X, because it's affecting Y, so it's a reflection in the x-axis. Good. So that 3/4 is the base, so I've already talked about that. Then I have that 3. That 3 is being multiplied up in that exponent, so that means it's a horizontal something. And would it be a horizontal stretch or compression? Compression, good, because x lies. And once a liar, always a liar, so x lies in everything. Horizontal compression by 1/3. Then that 2 means I go to the left, 2, and then down 1. All right, what questions do we have? Anything? We're good? Good, good, good. All right, so let's graph a few of these. We're not going to graph all of them, but we will start with number 1. So we're basically going to do the same thing we just did, even though it doesn't say that we have to. I'm going to find my parent function. So this is 3 to the x. That's more important this time than you may realize, because you got to make sure you can think about what the base is so you get your anchor points right. And so that means I know the parent function basically looks like that. Whether or not you want to write these other things out, it's up to you. I think it's probably a good idea. So this means we're going to go to the right 1, and we're going to go to down 4. First thing I want to take care of, because it's really kind of the easiest and it can help me make sure I'm doing things right, is my asymptote. So the asymptote for the parent function is at y equals 0. The only thing that's going to affect that is a vertical shift. And so since I go down 4, so does my asymptote. So I go to 1, 2, 3, 4. Here is my asymptote. Okay. So my parent function, my anchor points. Anchor points for the parent function would be 0, 1. Then from there, I'm going to go to the right 1 and down 1, 2, 3, 4. Right. So then since the base is 3, my next one will be at 1, 3. Then from there, I'm going to go to the right 1 and down 1, 2, 3, 4. Then when I have a negative 1, I'd be at 1/3. Then I'm going to go to the right 1 and down 1, 2, 3, 4. So those 3 points I have graphed. And then there's my function. My domain still is negative infinity to infinity. There's not really anything I'm going to be able to do to affect that, but I can definitely affect the range. Instead of going from 0 to infinity, I am now going from -4 to infinity. Y-intercept is something I graph, so I don't have to go calculate it. So think about what you think the Y-intercept is, and it's okay to have a mixed number here. It makes sense here. You're not taking an improper fraction and making it into a mixed number. It's what? 3 2/3. Good. So tell me how you came up with that, because there's 2 different ways to think about it. Okay. and you knew you went up 1/3, right? Yeah. Exactly. So we went up 1/3. So if I go down 1, 2, 3, I know I was up 1/3, so it's 3 2/3. Or you can think, okay, I'm here at 4, and I know I went up 1/3, so 4 minus 1/3. Either way, whatever. But it's 3 2/3. All right. So then my asymptote, we already decided we know it's at y equals -4. And because my domain is negative infinity to infinity, this would be infinity and negative infinity. Oh, yes. Dang it. I did that last period too. Yes, it's -3 2/3. Thank you very much. So worried about the number itself, I messed that up. So as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, what are we approaching? -4. Very good. All right, what questions do we have? Anything? All right, so then we're going to jump to number 4, which is actually on the next page if you're scrolling or whatever. So this is a natural base. So f of x is equal to e to the x, which means my basic parent function looks like that. I have 2 things going on. I'm going to reflect, and since it's affecting x, it's going to be in the y-axis. And then I'm going to go up 3. So I'm going to go ahead and take care of my asymptote. Since it was at y equals 0, we go up 3. It's up here. so let's start with our anchor points. We would start with 0, 1, reflect in the y-axis. Since I'm on the axis, I'm not going anywhere. And then I go up 1, 2, 3. When x is 1, my y value would be at about 2.7. I reflect in the y-axis, so I'm over here. And then I go up 1, 2, 3, which is off the graph, but not so much that I can't plot a point. Then remember, when x is negative 1, e is about 0.36, so I'm right here. I reflect in the y-axis, and then I go up 1, 2, 3. My function looks like this. Domain is still negative infinity to infinity because, again, there's really not much I can do, or not anything I can do to affect that with transformations. My range, I pushed up 3, so now I'm 3 to infinity. I do know my y-intercept. It's at 4, so 0, 4. My asymptote was at y equals 3. Then, since my domain is negative infinity to infinity, this is going to be infinity, negative infinity. So as x approaches infinity, what does f of x approach? As x gets bigger and bigger and bigger, y gets closer, closer, and closer to 3. Yes. And then as x approaches negative infinity, y approaches infinity. Any questions at all on that? Good. So let's look at 5. We have a fractional base here. So we've got f of x equals, so the base is 1/3 in parentheses to the x power, which means it's exponential decay. I have 3 transformations. So first I'm going to reflect in x-axis. That 2 means I have a horizontal compression because x lies by 1/2. And then that 1 means I go to the right 1. So I did not have any vertical shifts, didn't go up or down any, which means my asymptote stays right there at y equals 0. Get that in there. All right, so let's figure out our anchor points. When x is 0, y is 1 every time. I reflect in the x-axis, so it's going to come down here. Horizontal compression by 1/2, so since I'm on the axis, I don't go anywhere, and then I move to the right 1. When x is 1, y would be 1/3 for my parent function. I reflect in the x-axis, so it comes down here. Horizontal compression by 1/2, so my x value gets divided in half, and then I move to the right 1, and I'm right here. For my parent function, when x is negative 1, y would be 3. I would reflect in the x-axis, horizontal compression by 1/2, and then move to the right 1. It looks like this. All right, so my domain, still negative infinity to infinity. My range is now negative infinity to 0. Need a y-intercept. Well, I don't know what it is, but I know I'm going to have one. Like eventually it is going to intersect the the y-axis. So how do I find it algebraically? Do I substitute 0? Good, because your y-intercept is the y. You're looking for what is the y value when x is 0. So we want to find f of 0. If I set it equal to 0, that gives me my x-intercepts. So f of 0 equals, it's going to be negative, and then 1/3 to the 2 times negative 1 power. So it's basically negative, or 1/3 to the negative 2 power. That negative 1 reflects it and gives me 3, right? 3 squared is 9, but then I have to make it negative, so I get negative 9. asymptote is still y equals 0. This will be infinity and negative infinity. So as x approaches infinity, what is f of x approaching? 0. As x approaches infinity, f of x is approaching 0. And then as x approaches negative infinity, y approaches negative infinity. What questions do you have? We all good so far? All right, one more. We're going to graph another e. All right, so f of x is equal to e to the x power. I've got 3 transformations, so I've got that 1/3, so that is a horizontal stretch by 3, because x lies. That x minus 2 means I go to the left 2 and then down 1. So my asymptote does move because it had a vertical shift, right? So we're going to go down 1. So then I'm going to use my anchor points. I know when x is 0, y is 1. So I'm here. I'm going to go, I have a horizontal stretch by 3, but since I'm on the axis, nothing happens with that. Then I go to the left 2, and I go down 1. Then when x is 1, y is about 2.7. Horizontal stretch by 3. So my x value is 1, and multiply by 3, it becomes 3. Then I'm here, so then I go to the left 2, and then I go down 1. My last anchor point, when x is negative 1, y is about 0.36, so I'm right here. Horizontal stretch by 3, so my x value is negative 1, multiply by 3, I get negative 3. And then I go to the left 2 and down 1. My function looks something like this. Got stretched out. My domain's still negative infinity to infinity. My range is now negative 1 to infinity. Y-intercept, well, not allowed to just guess off the graph, especially when we're estimating things anyway. So I'm going to have to go calculate this one even though I have it graphed because I don't have an actual point there. So that's going to give me f of 0 equals e to the 1/3 power times 2 and then minus 1. So that gives me e to the 2/3 power minus 1. Do you have any clue off the top of your head what the value of e to the 2/3 power is? Nope, me either, okay? And you're not expected to. This is an exact form of an answer. This answer is what we want. We don't want you touching a calculator, okay? But I can tell you from my graph that this value should be a little bit less than 1. Wouldn't you agree with that? I mean, and that's what I think it is because, again, I know my graph ain't perfect. I will tell you, though, not that you would have to find this, but this does equal about 0.9477. And I think that jives with my graph pretty well, right? And so my y value here would be e to the 2/3 power minus 1. And sometimes your answers look weird, and it is what it is. My asymptote is at y equals negative 1. As x approaches infinity and negative infinity, so as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, what does f of x approach? Negative 1. What questions do you have? Anything? Okay. Alrighty, then your assignment is in Delta Math. So make good use of your time and let me know if you have any questions at all.